a charge separation between two quantities, there will be an electric field also between them from positive to negative. In order to increase the capacitance of a capacitor, or in this particular case, these two parallel plates, the only thing I can do is decrease the potential. Two plates separated by a distance of, let's say, d, and they have charge separation. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, Mysuru. And today we are going to discuss a few things about dielectrics. So what they are capable of, and how certain materials are made up of dielectrics. So what exactly are dielectrics? Basically, we can just say that dielectrics are materials which do not allow current to pass through them. That is, current to pass through them. That is, they are basically behaving like insulators. In short words, we can just say that dielectrics are sort of like insulators because they do not allow current to pass through them. Examples being like paper and mica. So these are a few examples of dielectrics. So basically dielectors are insulators because they do not allow electric current to pass through them. But we are more focused on their properties and how they behave under certain conditions. So in order to understand them a little more, we are going to dive in a bit deeper and look at their properties. So what exactly are the properties of dielectrics, and are there different types? And if so, how do they react under different conditions? So let's look at them. So basically, dielectrics are of two types. That is, one being polar and one being non-polar. We know that polarity means there is a difference of charges. So one being polar and one being non-polar can only mean one thing. There is a charge separation between one type of that dielectric, and in another type, there is no essential charge separation. So what does that look like? So what we are saying exactly is that there are certain materials known as polar dielectrics in which the charge centers do not coincide. They will have randomly oriented charge centers where the charges do not coincide with each other, meaning they are polar. That is, they do not have charge centers which coincide with each other. They have a slight polarity inside each sector. So in the case of non-polar molecules, we can just assume that they are charge centers which are coincide. So they have charge centers which are coincided perfectly at the center, meaning they do not have a polarity in them. So what will be the net dipole moment of these particles? But for the polar molecules, we don't even have to worry about dipole moment because innately the charge centers coincide with each other, meaning the dipole moment of these particles will be zero. Don't forget, what are dipoles? Dipoles are essentially two charges which are equal in magnitude but opposite in polarity, separated by a small distance. So the dipole moment will always be zero for a non-polar molecule because their charge centers coincide. One more thing you have to know about dielectrics is that when kept in an external electric field, these dielectrics will innately develop an electric field which is in the opposite direction of the electric field which is applied due to the polarization of charges. Before understanding that, let us look into the types and certain properties. So they are of two types, that is polar dielectrics and non-polar dielectrics. So we can essentially say that there are two types, polar and non-polar. For a polar dielectric, we can say that the dipole moment is not equal to zero because their charge centers do not coincide with each other. And for a non-polar dielectric, we can say that the charge centers coincide with each other, so the net dipole moment will be equal to 0. So what are the examples for a polar dielectric and non-polar dielectric? For a non-polar dielectric, we can take the case of, let's say, CO2 molecules, or we can even take the case of H2, any linear molecules where the charge centers coincide with each other. We can take it as an example for non-polar molecules, because these dielectrics are existing with us, amongst us in everyday life. So what essentially happens is that if there is a carbon atom in the center, O2 atoms are arranged in such a manner that the net charge or net dipole moment is 0. Same goes for the H2 molecules, because two H2s are arranged also in a linear fashion so that the net dipole moment of them cancels each other out and becomes 0. But in the case of a polar molecule, let's say water, we can say that water is a polar molecule, which means it has a slight imbalance in charge. It is very evident when you turn on a pipe and the water is running. If you rub a balloon to your head and keep it near the water, you can see that the stream of the water bends towards the balloon. That is because of polarization and the existence of a net dipole moment. This charge imbalance is what causes the water to change its path and become attracted to the balloon, which means that the net dipole moment is not 0, and it is an example for polar type dielectric. That is H2O and HCl. Basically, any ions, that is any particle or any molecule that carries a charge, will be an example for polar dielectric, which means that, again, if H is this, the arrangement of oxygen molecules will be at an angle, stating that there is a charge imbalance and a net small dipole moment existing among them. Similarly, for hydrochloric acid also, there is a net charge imbalance, which means that they have a net charge or net dipole moment. Now, what will be the net electric field because of these particles? We can say that the net electric field inside that particular particle, let's say a paper or a piece of mica or anything, if we take it, what will be the net electric field of that particular dielectric? For easiness, for understanding, imagination purposes, we can say that the dielectric we are taking is a drop of water and a drop of CO2 gas, or a small molecule or a small portion, 1 cubic centimeter cube of CO2 gas. However you want to picture it. If we take that particular unit of each material, we can see that the net electric field of both particles are 0, and that is because of very different reasons. The reason why a non-polar molecule has net electric field of 0 is because the charge centers coincide with each other. That is, positive and negative coincide with each other in a manner that the net electric field is cancelled out. But in the case of a polar molecule, the net electric field is 0 because of a very different reason. That is, even though the polar molecules are arranged in a manner that the charge centers do not coincide with each other, but still the charges are so randomly oriented that the net effect of the electric field developed is cancelled out. Even if individual domains will have an electric field, in the total sense, the net electric field will be cancelled out when we take the entire molecule. When we take the entire area we are considering, then we can see that the electric field, the net electric field, will be equal to 0 because the charge domains are randomly oriented. So, E net will be equal to 0, and here also E net will be equal to 0. And these two are because of two different reasons. One is because the charge centers are randomly oriented, so they cancel each other out. And here it is because the charge centers coincide with each other. So that means net electric field will become 0. Now what will happen if I place a piece of both polar and non-polar dielectric in the presence of an external electric field? That is what we are going to see right now. So we can say that, let's say this particular piece is a non-polar dielectric, and I'm going to keep this in the presence of an external electric field and see what happens. So I can see that this is an external electric field in which I am keeping the dielectric material. So initially the dielectric material, that is the polar dielectric material, will be in a manner so that the charge centers are randomly arranged. So there is no net electric field. Even though the charge centers do not coincide exactly, the net electric field will be 0. But when I apply an electric field through the dielectric, what will happen is that there will be polarization. That is, we studied that the positive charge will be along, the force experience for the positive charge will be along the electric field. So that means that the positive charges will have a tendency to crowd around in the direction of the electric field, while the negative charges will have a tendency to move away from the electric field being applied. So we can say that the negative charges will be arranged in a manner opposite to the electric field applied, and the positive charges will be crowded in the direction of the electric field being applied. So we can see that the electric fields, that is the positive and negative charge centers, align themselves according to the electric field being applied. Now there is an electric field being developed. So why? Because this particular area is now negatively charged, while this particular area is now positively charged. So we can see that when the electric field was applied, the charge separated from its initial state and aligned themselves according to the electric field, which caused it to develop a net electric field inside the dielectric. So now there is one negative side and one positive side. So the charge centers are aligned according to the electric field. When there is charge separation like this, this is known as polarization. And since there is one negative side and one positive side, there will be an electric field between those charged particles, and that particular electric field will be in the opposite direction. We know that electric field lines start from positive and seeks the negative charge. So if this side is positive and this side is negative, we can say that the internal electric field which is generated because of the electric field applied will be in the opposite direction of the external electric field, that is the electric field we applied. So this particular electric field which is generated because of the polarization of charges will be in the opposite direction of the external electric field. Let's say E0 is the external electric field. Then the internal electric field due to polarization will be in the opposite direction. So we can actually say that net E or E net will be equal to, let's say external electric field is E0, then we can say that the net electric field will be equal to E0 minus EP. And keep it in your mind, E0 minus EP is not equal to 0. There will be a net electric field because the electric field developed inside the dielectric is not strong enough to cancel out the external electric field, but it is strong enough to reduce it. So we can say that even though the polar dielectric was initially randomly oriented, having no net electric field, in the application of a net electric field, it polarizes and develops an internal electric field which is opposing the external electric field being applied, and the net electric field can be written as E naught minus EP. E naught being the external electric field and EP being the electric field developed inside the dielectric due to polarization. Now what about non-polar molecules? How will they behave? Interestingly, in a very similar manner. Even though the charge centers coincide with each other for a non-polar dielectric, the behavior of that non-polar dielectric will be very similar to that of a polar dielectric under the influence of external electric field. That is, even though the charge centers coincide with each other, initially and there is no net electric field, under the application of an electric field, polarization again occurs, which causes again an electric field due to polarization, which is in the opposite direction of the electric field being applied, generating another net electric field, and that will be equal to E naught minus EP, which is not equal to 0. So same principle, the only difference is that one was a non-polar dielectric and the other was a polar dielectric. The innate difference is that the charge centers coincided for one being non-polar, and for polar the charge centers do not coincide with each other, but the net electric field is 0 because of the randomness of their orientation. And polarization can be summarized as such. So we can say that divided by the total volume, that is P net by volume, will give you the total polarization. So we can write it as, the only thing you have to remember is that polarization P will be directly proportional to the electric field applied. The more the electric field is being applied, the magnitude of electric field is increasing, which means that the polarization will also increase. Charge separation will increase. So we can say that polarization will be directly proportional to the electric field being applied. And if you want to take away the proportionality sign, we can write it as P is equal to chi E. This particular symbol is known as chi, CHI, but it is read as chi, and it is known as the susceptibility factor, or you can also call it as electrical susceptibility. This term is known as electrical susceptibility, and that is indicated by the letter chi. So we can write it as P is equal to chi E. This is just an equation depicting how to calculate polarization, or just saying that polarization and electric field are related in this mathematical sense. Moving on, we have seen that many circuit boards, if you have ever broken a remote control or any electronic devices, there will be a green board and there will be materials like this sticking out of the electrical component board. So we have seen that, but we don't know what exactly those are. They had writings on them, they were in different shapes, but we did not know what they were. So essentially, these are known as capacitors. Capacitors has only one job to do, that is, they have to store electrical charge. In this particular case, we can say that capacitors are designed to store energy, and the way or the ability of which they store energy is known as capacitance. So here we are going to study the topic, that is capacitance. So we can say that these devices are known as capacitors, which stores electrical energy in this particular case. And we can generally say that capacitance is the ability to store energy. Capacitance is the ability to store energy, and these are examples of capacitors. They can be cylindrical in shape, they can be circular in shape, or they can even be rectangular in shape, depending on how they are made, because one is parallel plate capacitors, and the others are other examples of them. We will be focusing more on this particular guy, that is parallel plate capacitors. We will see that in very short time. So we have seen many writings on these capacitors. We can say that there is 1000 mu F. What is this 1000 mu F? There is another notations of 50 volts and everything, but what is this particular 1000 mu F? So we know that 1000 mu is nothing but 1000 into 10 raised to minus 6. Mu meaning micro. And what is this particular F? This is the SI unit of something. And that something here is nothing but capacitance, and F is nothing but farad. So farad is the unit of capacitance, and we can say that it is generally in the terms of microfarads, because if you have 1 farad, it will be really large. So if you have 1 farad, it will be really large. So we'll only deal with capacitance in terms of microfarads or nanofarads or going on like that. Basically, if you want to understand capacitors even more, you can relate it to an water tank. That is, imagine that in your house you have a water tank like this, or a cup, whatever you want to imagine it as. The purpose of that particular container is to store the amount of water given to it. So if we give the amount of water, then the purpose of this particular water tank or cup is to store that particular amount of water given to it to a particular limit. So it has a limit, it has its boundaries, and the purpose is to store something. In this particular case, it is a water tank, so it has to store water. So comparatively or analogous to this, we can say that the job of a capacitor is to store energy, and it has a particular limit and boundaries same as that of a water tank. That is, it can only store a certain amount of energy depending on its capacity. So how much capacity a certain thing has. So how much can it store? How much can it handle? That is the point and purpose of a capacitor, to store energy, and that particular device is known as capacitor, and the phenomenon is known as capacitance. Let us dive a bit deeper into capacitance and understand how this new entity is connected to the chapter name, that is potential and capacitance. So we have to deal with potential and capacitance. So we can say that potential of any system or anything will be proportional to the charge which is placed near it. If I place a 5 coulomb charge, the potential will be, let's say, V1. But if I place a 10 coulomb charge, the potential will be immensely high, meaning the V2 potential will be higher than that of V1. So we can write it as V is directly proportional to Q. If the Q is high, then the potential will also be high, meaning that the amount of potential I receive will solely depend on the magnitude of charge which is kept at a certain point. Now, again, this is a proportionality sign and we need it in the terms of an equation. So we can write it as Q is equal to CV. And that is how, ladies and gentlemen, capacitance came into existence. That is, this particular C is capacitance. And capacitance can be written as C is equal to Q by V. So this is the equation for capacitance. C is equal to Q by V. And this is a very important equation. CV is equal to Q, or Q by V is equal to C. Don't ever forget it. Now there is just one more problem. That is, if I want to increase the capacitance of certain things, what do I do? For example, if, let's say, I was living alone in a flat and I had a water tank which was like this, and I only needed about 20 liters of water. So it was a 20-liter tank. But after a while, a few of my friends came over and then cousins came over, and I needed like 50 liters of water. Then what do I do? So what I can do is increase the capacitance. So I had to increase the capacitance of that particular tank. So how do I do this in terms of capacitors? So if I want to increase the capacitance of a certain dielectric or capacitor, how do I exactly do it? So for that, we are going to look into the properties and we are going to find out how we can actually increase the capacitance of a certain material. So imagine that I have a sheet like this, and that particular sheet is positively charged. So I have kept a Q here, which is a source charge, making this particular sheet positively charged. So this is positively charged. And now what I'm going to do is take another conductor and keep it here. And because of the positive charges near that particular plate, it will develop polarization, making one side negatively charged and the other side positively charged. So I have charge separation now, and we are going back to the first chapter and introduce the concept of induction, and then we are going to do earthing in order to get rid of these particular charges. So we get a shape like this. Initially, I had positive charges, and then I kept one more sheet developing charge separation, and now I'm going to introduce the phenomenon of earthing or grounding, which means that all the positive charges from that side run off to the ground, and now I am left with nothing but a positive side and a negative side. So this entire side will vanish off into the ground, and I will be left with a plate which is positively charged and a plate which is negatively charged. So this will be minus Q, that is negative Q and positive Q. When there is a charge separation between two quantities, there will be an electric field also between them from positive to negative. Let's say they are at a distance D. So we can say that one plate is positively charged and one plate is negatively charged, and they are at a distance of D. So electric field will be from positive to negative. Now, why did I actually do that? Why did I actually make this particular plate like this? So remember when I said we are going to focus on a particular guy? That particular shape was this. That is this particular guy. This particular shape and this particular capacitor is known as parallel plate capacitors. That is, two plates are arranged in a manner so that it develops or it acts as a capacitor. Now, why did we do all of this? We did all of this in order to find out how can we increase the capacitance of any material. So in order to increase the capacitance of a capacitor, or in this particular case, these two parallel plates, the only thing I can do is decrease the potential. How and why will be shown in just a moment. So we can say that this particular plate will be at a potential V1 and this particular plate will be at a potential V2 because of their respective charges. Now, what will be the combined potential at, let's say, in this point, in the middle? So we know that the capacitance or the equation for the capacitance is given by Q times V, because we just found out C is equal to Q by V, which means that the capacitance and the potential are inversely related, which means if V increases, C decreases. So in order to increase capacitance, we have to decrease potential. So we know that they have a net potential between them, and if I want to increase the capacitance, I have to decrease the particular potential at this point. So in order for that, first we have to find the net potential. So net potential V is equal to V1 plus V2. So we can say that net V is equal to potential due to the positive charge, which is V2. Again, that is positive, but the potential due to the negative charge is negative. So we can write it as minus V1, meaning V2 minus V1 will be the net potential at that particular point, which means that I have decreased the potential of this particular plate so that it can store more. So that is why I brought a plate near this plate initially. So initially, let's say I had a charge plate at a particular potential V. That is, initially I had a plate which was charged positively and it had a potential of V. So capacitance was C is equal to Q by V. But my problem was the capacitance was fixed and I wanted to increase the capacitance, and the only way to do that was to decrease the potential. And how did we decrease the potential? So easy, we brought another plate near that, we grounded out the charge we did not want, and we created a charge separation between the two plates, which means there will be an electric field between them. And because of the charges are different and the potential between them are different, the net potential was given by the difference of the potentials of individual plates, meaning the net potential went down because it is V2 minus V1. So net V will be lower than the initial potential of a single plate. So we have increased the rate of capacitance for that particular plate. So the only thing we have to remember is that we can increase the capacitance of any substance by introducing a potential difference. We are exploiting the property that capacitance is inversely proportional to the potential difference, or inversely proportional to potential. Now let's take capacitance to a more mathematical level. We are going to find out what is the capacitance of a certain material. In this particular case, we are going to find out what is the capacitance of an isolated spherical conductor. So what is a spherical conductor? It is a round sphere which has uniform charges all spread out uniformly through the surface. So I have a sphere, let's say, of radius r. So I have a sphere of radius r in which charges are distributed evenly. I want to find out what is the net capacitance of that particular sphere. So, and we are considering that this particular sphere is isolated. Why it is being considered as isolated sphere is because we don't want any other material to interact with that and cause a disturbance in the potential of that particular system. That is why we are taking it as an isolated system. Just like when we are taking charges, we took point charges Q1, Q2, Q3 in space, in vacuum, where they are isolated. No other properties were disturbed. No other systems were disturbing our particular system. Just like that, this is an isolated sphere in space. So we can say that the net charge, let's say these are Q1, Q2, Q3 up to Qn, and we can say that the net charge of that particular sphere is given as Q. If there is a net charge, we can also say that there is a net potential, that is V. So we know that Q by V is nothing but C, which we are going to calculate. So in order to calculate the capacitance of that particular sphere which is having a radius r, first we write down the equation for capacitance, that is C is equal to Q by V. That is the first step we are going to do. And the next step is that we know that V has an equation of its own and we are going to substitute that. We know V is equal to KQ divided by R. So here we can write equation 1 as 1 becomes Q divided by V being expanded, that is V is equal to K, which is 1 by 4 pi epsilon naught, Q. This particular Q is nothing but the net charge which is equal to this Q. So KQ divided by R. This R is nothing but the radius of the sphere, so R. So what will we get? R will go to the numerator, Q and Q will cancel each other out, implies we get R divided by K, and K is nothing but 1 by 4 pi epsilon naught. So we can write that as 1 by 4 pi epsilon naught, meaning this 4 pi epsilon naught will go to the numerator. So we can write it as 4 pi epsilon naught R is equal to C. So what do you understand from this? The capacitance of that particular isolated sphere in space is nothing but 4 pi epsilon naught R. So all these are mathematical quantities or constants. They don't affect the capacitance of that particular sphere. The only thing that affects the capacitance of that particular sphere is the radius. If the radius increases or decreases, the capacitance is affected. Otherwise, it remains unaffected by the concentration of charge or any other properties. So what use do we have for that particular equation? That is, C is equal to 4 pi epsilon naught R. What use do we have for this equation? For example, some random person comes up to you and say, remember Earth, the planet we live in, what will be the capacitance of Earth? Let's say for argument's sake. Then you can clearly say that, well, according to physics, I know that the equations for capacitance is 4 pi epsilon naught R, and I know the radius of the Earth clearly to be approximately equal to 6400 kilometers. It is actually 6370 something kilometers in radius, but for approximation sakes, we can say that it is 6400 kilometers. And we don't need any other factor, only the radius is the thing affecting the capacitance of a certain material. So we can substitute that directly here and we'll get, voila, the capacitance of Earth to be 711 microfarad, because the unit of capacitance is nothing but farad. You can do the calculations if you want. It is 6400 into 10 raised to 3 meters, and 4 pi epsilon naught is nothing but 9 into 10 raised to 9. Or you can individually add that. Epsilon naught has a value of 8.854 into 10 raised to minus 12. So you can substitute the individual values here and you can find the capacitance of Earth. So for pi, you know 4, you know pi, which is 3.14, epsilon naught is nothing but 8.85 into 10 raised to minus 12, and then R is nothing but 6400 kilometers, or you know the value of K, you know the radius of the Earth, and the capacitance will come right out to be 711 microfarad. So one question will be, Earth, such a huge planet, has such small capacitance? Well, actually no, because this capacitance is actually capacitance C is equal to Q by V. This clearly states that how much of charge is required to raise the potential by 1 volt. That is what we are calculating here. So in actuality, the Earth has a lot of capacity, but in this particular case, we are calculating how much charge will be required to raise the potential by 1 volt, and that will be equal to the capacitance. So we need 711 microfarad to increase the capacitance of Earth by 1 volt. So this example was given because it has been asked in your annual examinations. Find the capacitance of Earth. It is fairly simple. It is just one equation and substitution and you'll get the value right out. So that is why I discussed this as an example for the application of finding out the capacitance for an isolated spherical shell. So finally, we are going to discuss about the hero of the day, that is parallel plate capacitors. Parallel plate capacitors are nothing but two plates separated by a distance of, let's say, d, and they have charge separation. Remember how we created two plates 5 minutes ago by earthing the extra charges off? So one was Q and one was negative Q, each having its individual potential, and the net potential was found out to be less than both of their potentials combined. But the important thing we have to remember here is that since there is charge separation like this, there will be an electric field acting in between those two plates. So we can say that the electric field will be from positive to negative. So this will be the direction of the electric field between those two plates. And we are going back to the first chapter again to consider the surface charge density sigma. Since there will be a number of charges on the surface of this particular plate or sheet, we have to consider surface charge density. Surface charge density is nothing but sigma. So sigma, if you don't remember, it was Q by A. So here we are going to calculate what is the electric field between those two particular plates. For that parallel plate capacitor, we are going to calculate what is the electric field between them. In order to calculate that, we need sigma, that is surface charge density. If you remember from the first chapter, we had calculated something very similar to this for a single sheet. Now we are going to calculate what happens if another sheet is placed right beside it. It will become a capacitor, and here we are going to calculate what will be the electric field between those two parallel plates. So we can say that E will be equal to E1 plus E2. Why E1 plus E2? That is clearly because of this positive charge there is an electric field, and because of the negative charge there is an electric field, which means the net electric field at the center will be equal to the individual sum of electric field due to positive Q and electric field due to negative Q. Let's say for argument's sakes both are equal at this point. Even then we have to write it as E is equal to sigma divided by 2 epsilon naught. If you remember the first chapter under Gauss's law applications, we found this statement or this proof for the electric field due to a plain uniformly charged sheet. Now we have two sheets E1 and E2. So we can write it as E1 plus E2 is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. So how much will this be? Sigma sigma is common, take it outside. 1 by 2 plus 1 by 2. Sigma by epsilon 1 by 2 plus 1 by 2. Half plus half is 1. So we can just say that net E is equal to sigma by epsilon for a parallel plate capacitor. Wait. We are not done yet. So now we have found this result. We are not going to stop just there, because we know that sigma is equal to Q by A. So we can write E is again equal to Q by A epsilon naught. And now can we stop here? Of course not, we are not stopping here, because we know two more equations, that is C is equal to Q by V or Q is equal to CV. And we know another equation for E also, that is E is equal to minus dV by dr. Minus sign just indicates the direction, so we can neglect it for now. So the initial point is that it is potential divided by distance. In this particular case, the distance is d. So we can write E is equal to V by d. And we also have an equation for capacitance, which is Q by V also. So first we are going to take this particular equation and we are going to include it right there. We can write it as E is equal to sigma by 2 epsilon naught. This was E1. We had another one which was E2. So which is equal to E2 also. So net E was written as E1 plus E2, and that was equal to sigma by epsilon naught. So that was the first result. But we knew that sigma is equal to Q by A. So that can be added to this equation, and that can be written as E is equal to Q by A epsilon naught. But we also knew that the equation for capacitance C is equal to Q by V, and the equation for V is equal to or given by, from the formula, E is equal to dV by dr, or it can be simply written as V by d, potential by distance. So E into d will give us V. So this was used here and written here. So E into d. But we already found out what E was. E was equal to Q by A epsilon naught. We already found out that E into d was equal to V. So now since this is established, we are going to substitute all these results into C is equal to Q by V. So in order to find out C, we are going to incorporate all these results into that particular equation. So we can write it as C is equal to Q by V, E is equal to Q by A epsilon naught. And now we know that E is equal to E into D is equal to V. So we just multiply here with a D and we'll get an equation for E. So we can just write this as Q by QD divided by A epsilon naught, and then these two cancel each other out, and finally we are left with the equation A epsilon naught divided by D, that is equal to capacitance, because this will go to the numerator and D will be in the denominator. So we can write it as A epsilon naught divided by D is equal to capacitance. That is all for today. I hope you have understood about parallel plate capacitors, capacitance, and certain potential things that you need to understand. So I'll see you all in the next class. Until then, thank you.